Security breach detected. Watch as this RSA 2048 encryption, the guardian of internet security, comes under attack. Quantum computing strikes from all directions. The lock changes color, the shackle breaks open, the encryption is cracked. Quantum decryption, why classical encryption will fall. What is encryption? Encryption transforms readable data into unreadable code. It starts with plain text, like "Hello World." Using a secret key, this plain text is converted into ciphertext, an unreadable jumble of characters. Only someone with the correct key can reverse this process to read the original message. RSA encryption, the guardian of internet security. RSA is one of the most widely used encryption systems. Its security relies on a simple equation, n equals p times q, where p and q are large prime numbers. N is the public key component, but finding p and q from n is extremely hard. In fact, RSA 2048 would take billions of years to crack using classical computers. The prime factorization problem. What is 15 made of? Simple. 15 equals 3 times 5. That was easy, only 2 divisions needed. But now try this, RSA 2048. A 617-digit number, 2048 bits, the product of 2 unknown primes. A classical computer must try dividing by billions of possible factors. Brute force attack, checking 2, 3, 4, and billions more. How long would it take? The age of the universe is 13.8 billion years. Cracking RSA 2048 would take over 300 trillion years. That's 21,000 times longer than the universe has existed. Classical computers simply cannot do this. How classical computers work. The classical bit is a transistor, a simple switch that can be either off, representing 0, or on, representing 1. One bit equals one state at a time. In binary counting, an 8-bit number can represent values from 0 to 255, that's 256 possible combinations. But here's the problem: to find one solution among 256 possibilities, a classical computer must check each one sequentially. For RSA 2048, that means checking more possibilities than atoms in the observable universe. Enter the quantum bit. A classical bit can be 0 or 1. But a quantum bit, or qubit, can be 0 and 1 at the same time. This is called superposition. The block sphere visualizes all possible qubit states. At the top we have state 0, at the bottom state 1. But the state vector can point anywhere on this sphere. The equation alpha 0 plus beta 1 represents any point on the sphere as a valid qubit state. Infinite possible states exist between 0 and 1. Superposition, the quantum advantage. With classical computing, one bit stores one state. With quantum computing, one qubit explores multiple states simultaneously. Let's see the scaling. 2 classical bits give us 4 states to check one by one. 2 qubits explore all 4 states simultaneously. 10 bits mean 1024 sequential checks classically, but 10 qubits explore 1024 states at once. And here's the exponential power: 50 qubits can explore over 1 quadrillion states simultaneously. This is quantum parallelism. Quantum entanglement, the spooky connection. Einstein called it spooky action at a distance. When 2 qubits become entangled, measuring one instantly affects the other, no matter the distance. Watch as qubit A and qubit B become entangled. This Bell state represents maximal entanglement. Now, when we measure qubit A and get result 0, instantly qubit B also becomes 0. 100% correlated, no matter the distance. This enables powerful quantum algorithms. Shor's algorithm, the RSA killer. In 1994, Peter Shor at AT&T Bell Labs made a groundbreaking discovery. He found an algorithm that could break RSA encryption using a quantum computer. Shor realized that finding the period of a function could reveal the factors of large numbers. The key insight: exponential classical operations become polynomial quantum operations. Compare the complexity: classical factoring is exponential, taking 10 to the power of 15 years. Quantum factoring with Shor's algorithm takes only hours. Quantum computers can break RSA. How Shor's algorithm works. Step 1. Choose a random number less than n. Step 2. Use the quantum computer to find period r. This is where quantum computers shine. Step 3. Calculate the greatest common divisor of a to the power r over 2, plus or minus 1, and n. Step 4. Get the factors of n. The quantum part, finding the period, is exponentially faster than any classical method. Quantum Fourier transform, the heart of Shor's algorithm. The QFT transforms quantum states to reveal hidden periodicities. Watch as we combine different wave frequencies. Just as a prism separates light into colors, the quantum Fourier transform separates quantum states into their periodic components. QFT finds the hidden period that reveals the factors. Quantum state space. A single qubit exists in a three-dimensional state space, represented by the block sphere. The x, y, and z-axes define this space. The state vector can point in any direction, representing infinite possible states. As we rotate around, you can see the full scope of quantum possibilities. Qubits exist in this infinite state space, giving quantum computers their remarkable power. Factoring time comparison. How long to break RSA encryption? For 512-bit keys, classical computers take about 1 hour, quantum takes about 1 second. For 1024-bit keys, classical takes about 1000 years, quantum takes only 10 seconds. For 2048-bit keys, classical takes 10 to the power of 15 years, but quantum takes only 1 minute. That's 10 to the power of 15 times faster. Shor's algorithm makes RSA encryption obsolete. The current state of quantum computing. IBM's quantum computers now have over 1,000 qubits. Google achieved quantum supremacy in 2019, performing a calculation in 200 seconds that would take classical supercomputers 10,000 years. But challenges remain: noise, error rates, and maintaining coherence. Still, progress is exponential. Experts estimate cryptographically relevant quantum computers within 10 to 20 years. Required qubits for RSA. To break different RSA key sizes, we need different numbers of logical qubits. RSA 1024 requires about 2,000 logical qubits. RSA 2048 requires about 4,000 logical qubits. RSA 4096 requires about 8,000 logical qubits. Current quantum computers have thousands of physical qubits, but logical qubits require error correction. The gap is closing rapidly. Post-quantum cryptography, the defense. Organizations worldwide are preparing quantum-resistant encryption. Lattice-based cryptography uses hard problems in high-dimensional lattices. Hash-based signatures rely on secure hash functions. Code-based cryptography uses error-correcting codes. NIST has already standardized new post-quantum algorithms. The transition must begin now. Harvest now, decrypt later. Here's a chilling scenario. Adversaries today are collecting encrypted data and storing it. When powerful quantum computers arrive in 10 to 20 years, they will decrypt all that stored data. Bank records, government secrets, personal information, all exposed. This is why we must transition to quantum-safe cryptography now, not later. Why quantum computers for decryption? Let's summarize the quantum advantages. Superposition allows testing many solutions simultaneously. Entanglement correlates quantum operations. Quantum parallelism provides exponential speedup. Shor's algorithm enables efficient period finding. The result: polynomial time versus exponential time. From billions of years to mere hours. Classical computers cannot match this efficiency. The race is on. Quantum computers versus post-quantum cryptography. On one side, quantum hardware advances rapidly, getting more qubits, lower error rates, longer coherence times. On the other side, cryptographers develop new quantum-resistant algorithms. Currently, cryptography is winning. But for how long? The race to secure our digital future continues. The quantum threat is real. Current encryption will eventually fall. Only quantum computers have the mathematical advantage to break modern cryptography. The transition to quantum-safe cryptography must happen now. Prepare for the quantum era. Like and subscribe for more quantum content.